8.3 Lesson 1, Trigonometric Integrals. Our objective for today is you'll be able to solve trigonometric integrals involving powers of sine and cosine. We will be seeing that some of our examples will require us to do integration by substitution, but we have to be a little bit clever to first see what substitution we would have to do by manipulating the integrand using Pythagorean identities. And then there are some other problems where you will instead be using a power reducing formula. So a common theme for the problems from today's examples would be rewriting the integrand using some trig identities and then going from there using integration by substitution if needed or solving if not needed. These are some guidelines that you can follow for evaluating integrals involving sine and cosine. These are from your textbook, I believe the first page of section 8.3. So now you're going to take a look at these guidelines, but actually after you've seen a couple of examples, you don't need to look at these guidelines. You'll just have an intuition for what to do after seeing a couple of examples. But if you wanted to look at this to begin with, if you have the integrand that's a product of sine and cosine factors, and the power of sine is odd and positive, save one sine factor and convert the remaining factors to cosines, and you have something similar for the second guideline, but the power of cosine is odd and positive. Save one cosine factor and convert the remaining factors to sines. We will actually see these two guidelines applied in two of our examples. And then the third guideline is if the powers of both sine and cosine are even and non-negative, make repeated use of these power reducing formulas to convert the integrand to odd powers of the cosine. And then if necessary, do what you would do in guideline 2, or maybe you have a simpler problem that you can solve without having to do this. Here's our first example. Find the integral number 6. We have the indefinite integral of cosine cubed x times sine to the fourth x dx. So we are going to use integration by substitution here. We're going to let u be equal to sine of x. But to make the substitution work out so that we can change variables, you will have to manipulate the integrand as follows. We're trying to use the substitution let u be equal to sine x. So to be able to change variables, we will need to have cosine x dx as a factor in our integrand. We have cosine to the third power. So what we need to do first is rewrite cosine to the third power as cosine x times cosine squared x. And then we have sine to the fourth x dx. The next step is to use a Pythagorean identity to rewrite cosine squared x. So using this Pythagorean identity, we can write cosine squared x is equal to 1 minus sine squared x. So that gives us cosine x times 1 minus sine squared x times sine to the fourth x dx. And now we can go ahead and use our substitution. Let u be equal to sine x. So wherever I see sine x, I will replace with u. And because I have rewritten my integrand, I see cosine x dx, which will allow me to make the substitution du and change variables from x to u. So now this is our next step. This is called the change of variables step. Cosine x dx becomes du. And then I have sine to the fourth x. That would be u to the fourth. And then I have 1 minus sine squared x. And that would be 1 minus u squared. So Now this problem is very easy to do. You're just going to use the power rule for integration, but before you do that, make sure you rewrite the integrand by distributing the u to the fourth. So we have u to the fourth minus u to the sixth for our integrand, and we can integrate using the power rule for integration. So you will have u to the fifth over 5 minus u to the seventh over 7 plus a constant of integration. But for your final answer, you need to go back to your original variable of integration, which is of course x. So what is u? U is sine x. So you will replace u with sine x, and your final answer will be sine to the fifth x over 5 minus sine to the seventh x over 7 plus c. Number 8, find the integral. We have the indefinite integral of sine to the third power, sine cubed x dx. And when you look at this, you might think, what can I do here? Can I do a u substitution? Can I let u be equal to sine x? If you try to use the substitution let u be equal to sine x, because the differential of u is cosine x dx, you will need to have cosine x dx in your integrand for the substitution to work out and allow you to change variables. We can make that happen by rewriting the integrand as follows. We can write the integrand as sine squared x times sine x dx. And then we will have to use our Pythagorean identity to rewrite sine squared x. So we can write sine squared x as 1 minus cosine squared x. So now our integrand will become 1 minus cosine squared x times sine x dx. So the substitution that I was originally thinking about is not appropriate for this problem. But instead of letting u be equal to sine x, I can let u be equal to cosine x, and I would be able to do this problem easily. Because right now I don't have cosine x dx, I have sine x dx. So I don't want to let u be equal to sine x, I want to let u be equal to cosine x. Then du will be the derivative of cosine would be negative sine x dx. And that will work out because I have sine x dx as a factor in my integrand, and I have sine x dx here. So if I multiply both sides of the equation by -1, then I'll have -1 times du is sine x dx. So now I'm able to change variables, and I will have 1 minus cosine x is u, so I have 1 minus u squared, and sine x dx is -1 times du, so I have a factor of -1, and I have du. And when I distribute the -1 to the rest of my integrand, that gives me u squared minus 1 du. And now this is really easy to do. I will integrate with respect to u by using the power rule for integration. So I have u to the third over 3 minus u plus a constant of integration. To complete the problem, all you're going to do is you're going to replace u with cosine x, and you'll have cosine to the third x over 3 minus cosine x plus c. So here we have number 14. We want to find the indefinite integral of sine squared 2x dx. A u substitution would not really work out here because you wouldn't be able to change variables. But what you can do is use a power reducing formula to rewrite the integrand. This would be consistent with guideline number 3 from the guidelines that we looked at the beginning of the lesson. And in fact, this is something that we've seen from chapter 10 when we were finding the area of a region bounded by a polar curve. So let's go ahead and rewrite the integrand using the power reducing formula for sine squared u. One thing to note is whatever the angle u is, you will have twice that when you rewrite that. So in our example, the angle u is 2x. So twice 2x is 4x. And I'm able to rewrite my integrand as sine squared 2x becomes 1 minus cosine of twice 2x, which is 4x, over 2, and then I have dx. The over 2, that's the same as multiplying the numerator by 1/2, and 1/2 is a constant, so I can factor it out. So now I have 1 minus cosine 4x dx, and I can integrate term by term. With respect to x, there's no need to do a u substitution for this problem. So we will have 1/2 times. When you integrate 1 with respect to x, the antiderivative would be x. And when you integrate cosine of 4x with respect to x, the antiderivative would be sine of 4x over 4. Now why do you need the over 4? Because if you just have sine of 4x and you differentiate that with respect to x, the derivative will be cosine of 4x, and then you'll have to use the chain rule and multiply by the derivative of 4x, which is 4, resulting in 4 times cosine of 4x, but we want 1 times cosine of 4x, so we compensate by dividing by 4. And of course, the derivative of sine is cosine, so it is appropriate for us to have that minus sign there. This is acceptable as your final answer. You can write it in different equivalent forms, and that's not something that you need to do unless you're taking a multiple choice exam and you get this as your answer, but maybe it doesn't exactly match with one of the choices. So now you'd have to see which of the choices is equivalent to this answer by maybe perhaps doing some algebraic manipulations. So today we looked at solving trigonometric integrals involving powers of sine and cosine. And we looked at 3 examples for that.